Hey everyone, so welcome to the first lecture of organic reaction mechanisms. So in this first phase, we will be discussing how to draw Lewis structures, calculating the formal charge, the degree of unsaturation, identifying the geometry and hybridization in organic molecules, and the effects of the electronegativity differences and the dipoles. Okay, so let's just start with this wonderful paragraph from Claydon. Now, you are already a highly skilled organic chemist because as you are reading these words, your eyes are using an organic compound retinal to convert visible light into nerve impulses. Right, when you picked up this book, your muscles were doing chemical reactions on sugars to give you the energy you needed. And as you understand, gaps between your brain cells are being bridged by simple organic molecules which are known as neurotransmitter amines, so that the nerve impulses can be passed around your brain. And you did all that without consciously thinking about it. You do not yet understand these processes in your mind as well as you can carry them out in your brain and body. You are not alone there. No organic chemist, however brilliant, understand the detailed chemical working of the human mind or body very well. So that's what it's all about, right? So organic chemistry is a beautiful course, but yes, we have our limits while defining the mechanisms or the reaction pathways or the fundamentals, but we'll try to cover as much as we can, which enables us to understand the basics and helping in problem solving. Now, the first, drawing the Lewis structures. So one of the very fundamental part of organic is being able to draw a molecule, okay, in the Lewis structure form. First rule that you have to remember, because if you try to find the method, the ideal method of how to write Lewis structures, you'll find various different methods or the sequence or rules, but it's all about practice because Lewis structures are not the absolutely correct thing, okay. The more you practice, you'll have your own set of rules. So it's not that you have to go by my rules only or somebody else's. It's just whatever makes you feel comfortable, right? So first, I suggest that you learn and remember the valence of commonly used elements. Like alkali metal, they all have valence of 1. Alkaline earth metal, they all have valence of 2. Aluminium has a valence of 3. Hydrogen 1, carbon 4, nitrogen, phosphorus, group 5, they have a valence of 5. Oxygen 2, halogens goes from 1 to 7. Sulfur goes from 2 to 6. So this valence will help you while making different bonds, right? Where you can extend the octet, where you cannot. Second thing, keep the higher valence atom at the central atom, because the atom which has higher valence can make more number of bonds. So it is like it feels better to put that in the central position, but it's not always correct. Sometimes the atom with the higher valence may be in the periphery. It may not always be in the central position, but yeah, as a general rule, yeah, we'll try to keep that in the central position. For example, here CH4, the carbon has a valence of 4. It formed 4 bonds, but hydrogen can form only 1 bond. So that is why hydrogen and fluorine, right? Hydrogen and fluorine are always at the periphery, because they can never be at the center. Why? Because the center has some needs something on the left and the right, on both sides. But hydrogen and fluorine, they cannot make more than 1 bond. Similarly, carbon here can make 4 bonds, 1 double and 2 single. Again, sulfur. So in this molecule H2SO4, sulfur has highest valence, 6. Oxygen also has a valence of 6, but oxygen cannot make 6 bonds. It only makes 2 because it has a limit of octet. It cannot exceed its octet due to the unavailability of empty d orbitals. So sulfur is placed in the central position and now it is forming 2 double bonds and 2 single bonds. So draw all these structures, practice these, because if you know the structure, only then you can draw it. You just can't imagine a structure. Okay, yeah, it can be like this also. No, it is the way it is. Okay, so you have to memorize. Third, never make more than 4 bonds for elements of second period, because the second period elements, they don't have empty d orbitals. So we cannot exceed their octet. Like nitrogen here, it has a 5 valence electrons, but it makes only 3 single bonds, sigma bonds, and 1 lone pair. Oxygen keeps 2 lone pair and forms 2 sigma bonds, right? But sulfur, it is not a member of second period. It can make more than like 2 bond, 3 bond, 4 bond, 6 bonds, right? Phosphorus, it has empty d orbitals. It can also go beyond the octet limitation. So just note on these structures, practice them. Then fourth one, start with the central atom and use the total available valence electrons to fulfill the bonding requirements, and try to keep the octet filled in all the cases. For example, in CH3NH2, how will you draw the structure of this CH3NH2? Let us start with carbon. So carbon we keep in the center position, then 3 hydrogen, so 3 electrons here, hydrogen, 1 electron from hydrogen side, and 4th electron of carbon is bonded with nitrogen. Nitrogen again, it can form total 3 bonds. So here, and 1 lone pair, right? So carbon has a total valence of 4, 3 hydrogen has total 3, nitrogen has 5, and 2 hydrogen has 2. So total we have 5, 8, 14 electrons available. So we have to distribute all these 14. So 2, 4, 6, 2, 4, 6, 8, 10, 12, 14. So yes, we have utilized all 14 electrons and all the octets are complete. Now in the carbonate, the carbon has valence of 4, oxygen valence is 6, so 3 oxygen, 18, 2 negative charge, so additional 2, so 20, 24. So in the carbonate, let's put carbon at the center, 1 oxygen, another oxygen, another oxygen. So carbon uses, so we have total 24 electrons to be used. How many pairs? We can have total 12 pair. So we used 3 pair of electrons already here. Then let's put 2 pair here. Now the carbon doesn't have a complete octet, so 1 must be a double bond. So now we have 2, 3, 4, 5, 6, 7, 8, 8 pairs, 9, 10. Okay, anything else we need? Yeah, we still need 2 more pair to be adjusted. So 1 here, 1 here, right? And 2 negative charge. The whole structure had 2 negative charge. So you can draw carbonate. Similarly, you can draw HNO3, carbon monoxide. So this is homework for you. You have to try and draw structures for HNO3, carbon monoxide, NO2 and HCN. And then in the next lesson, I'll discuss the bonding pattern of boron, carbon, nitrogen, oxygen and halogen. How the bonding totally depends on the valence electron. It doesn't depend on the nature of the atom. Whether it is boron or carbon or nitrogen or oxygen, it just depends on how many electrons the particular atom has for the bonding arrangements, right? So see you in the next class. If you like this video, then do share it with your friends, and any kind of feedback, let me know in the comment section. Thank you. Have a nice day.